That's how you waste time. Hey guys, welcome to another episode of This Is Your Lab. I'm your host, Dr. T, and today we have Alex. He knows this experiment pretty well. He's done it before in the past. In today's lab, we're going to be going over centripetal force and its role in circular motion. We'll be studying how centripetal forces actually act towards the center of a circular pathway, and confirming that the acceleration is centripetal, and we're going to confirm that there's a relationship between centripetal force, the tangential speed of an object going in a circular pathway, and the radius of that circular pathway overall. But before we do, let's go ahead and talk about today's pre-lab. For today's pre-lab, you're going to test the theory. Is it really centrifugal force or centripetal force? Is there an outward force or is there an inward force? Newton's second law. Remember that the direction of acceleration is the same as the direction of the force. So what we're going to do is use the Firefox app. We're going to go back into acceleration without G, as we've been using. And this time, you want to hold the phone exactly as you would be chit-chatting with a friend or, FaceTiming or what have you. Make sure that your Y orientation is outward from your hand, and X is going towards your thumb. That means Z coming out of your palm. Once you're confirmed in that configuration, you will push play, slowly move into position up here, hold for a few moments, and then slowly bring back down. Once you pause the data, you should be able to very easily confirm which axis underwent the most acceleration. If you weren't able to analyze your experiment right after you took it, you can save the experiment state, come back to it a little bit later. It'll show up as blue listed objects. You see I've got centripetal acceleration from that experiment you just watched. And here we are. Now remember that the orientation of the phone is very critical in that case. You held the phone in such a way that you moved in an arc with the y-axis pointing outwardly. If centrifugal force is a real force, then the acceleration should be positive. But if centrifugal force is fake and centripetal force is the thing, then our acceleration should be negative. Now this is just noise along the z-axis. There's something going on with the x-axis. That's true because we accelerated going up and down moving our hands, but we're more interested in the y-axis. So let's zoom in on that. And this time you take this picture. This will be the one. When you zoom in there, we don't need anything else, but you want to stay within there. You can see the zero, you can see the maximum accelerations, but this is very clearly a negative acceleration because the bottom of your phone, and make sure your orientations are good when you do it, the bottom of your phone was pointing towards your own person, acting as the line of centripetal force, and that the acceleration was pointing towards your center of person. You zoom in a bit, make sure you keep a little bit that shows that it was zero otherwise, and print this just to be on the safe side. You can save your experimental state in this case and come back to it later. We already done that. If you'd like to see how far you did go to more tools. You can look for the linear fit, and it will put a line up here, and then you pick your data and you touch right here at the point and you draw a line to the highest point. It'll tell you. Because it's acceleration versus time, we're looking at the maximum difference. That's minus 41 meters per second. You can also zoom this out further and see that you're out at 64 meters per second squared at your as your maximum when you're swinging through. Once you have your data and you've satisfied demonstrating that your acceleration was negative, centripetal acceleration does point towards the body, go ahead and capture your picture and transfer it to your laptop or whatever, and edit it, put it into Microsoft Paint, hit that inverse colors if you've got that. If you can't do that, go to the website that's made available on D2L, and you can invert that color so it goes easier on your easier printing at that same case. So that's using this exercise to confirm centripetal acceleration for your pre-lab. So the topic that we're entering into, circular motion, may seem a little bit uneasy, bizarre, peculiar, because we've been working with straight lines so far, and now we're getting into circular motion, and the variables are different. The equations seem to be a little bit new, but consider the possibility that they may actually be more similar than you expect. Let's take, for instance, the concept of arc length. If I want to measure an arc length on this ball, for example, from this point to this point, I would take a string, lay it across, and that will be the length here, this distance across the edge of the circle to one point, from one point to another. And if you think about this as a circle with a center, then this is at some radius, and this is some angle distance that is carved out between one point and the other. We refer to this as arc length. And if we take this string and we lay it across a meter stick, we can measure the linear length to that. And so the relationship between arc length and the angle and the radius is given by the direct relationship S equals r theta, where S is a linear quantity, r is a linear quantity, angle is an angular quantity. Well, just as we can do with a position, a change of position will be a velocity, so distance over time, v, is equal to r. The radius doesn't change for a circle, but the angular position can change, and we refer to that as angular displacement or angular speed. And then linear acceleration would be related to angular acceleration, again by a ratio of the radius of the circle, or circular path, if you will. So I've got written up here for you the linear qualities and the angular qualities, and when you put them side by side, you can actually see that they actually mirror each other very nicely. You have linear displacement, angular displacement, linear speed or velocity, angular speed, also angular velocity, but the angle is always in that angular direction. So we don't talk about the vector quality quite as much. It is there, but because it's all going in one direction, or the reverse of that, it's kind of redundant. It doesn't tell us anything new. Linear acceleration, angular acceleration. And just for clarification, so this is the angle theta, and this is the angle, and just for clarification, just to kind of help you navigate the letters, this is the Greek letter theta, this is the Greek letter omega, not a W, but it's similar to a W, but you kind of write it a little bit different. And then the alpha, like an A, you just make it look like you can just make it look like an X that you don't lift the pen off the page. And that's the letters that we're working with right now. You see the linear kinematic equations are familiar. Well, when you make the substitution of these quantities into your linear kinematic equations, the radius drops out, and you end up with identical forms with just using the angular quantities, theta, omega, and alpha. So now that we have taken a look at circular motion itself, the basics of the motion, and shown that the kinematic equations are very directly related to the linear kinematic equations, let's talk about Newton's laws. At least in particular, Newton's second law, because, as you can see, Newton's first law would prefer you go in a straight line. Remember, Newton's first law says an object in motion, which we assume is a straight line motion, an object in a straight line motion continues in that way unless acted upon by an external unbalanced force. So here's our mass that we have tied to some string that's going around in a circle. Well, the simple fact that it wants to go in a straight line that's Newton's first law. That's the concept of inertia. And so the mass wants to go in a straight line. The string, however, prevents that from happening, and let's explore what that means. So this mass difference here, this means that the path is changing. It can be going the same speed, but if the path is changing, that too corresponds to a changing vector, and a changing vector is enough for us to qualify for acceleration. So let's take a look at the acceleration concepts here. Newton's second law, written straightforward, F equals ma. In this case, we're going to consider just the one force that's causing it to change motion, where the single force acting on a single mass undergoing circular motion is going to accelerate somehow. How do we accelerate it? Well, the relationship that is not derived right now, but you should have access to, at least through resources I've made available to you. Centripetal acceleration can be described as the tangential speed, the speed at that surface point, at that point in time, squared, which makes it now a scalar quantity, over r. Again, r is the radius of the circular pathway. So we substitute that in, we get centripetal force defined as mv squared over r. Now, formally, we would write it in this way. If force is a vector, mass v squared over r, these are all scalar quantities, but it's still a vector force, so we have to represent that with an r hat. If you've done the x hat and the y hat in lecture, that simply means that x hat is a vector that goes in this direction along the x-axis, and it's only a unit vector. its length is 1, which means that all it does is point that direction. The y hat goes vertically, goes along the y-axis. Again, unit vector of length 1, so that it doesn't change anything, it just shows you the direction. So an r vector, r hat vector, would be pointing outward anywhere from this center point. Now in this case, it's positive, always positive. There's no such thing as a negative r hat vector. Everything originates from the center of your point where that vector originates, always pointing outward. So when you see here, the force vector is equal to negative r hat, that means that the force vector is pointing inward towards the center at that point on the circle. But this is something you contemplate. Just think about it. But as far as practice and what you're going to do, this is the one you want to remember. This just kind of background information. This is the guy. Okay, so now that we've looked at Newton's second law as a centripetal force, a force acting inwardly causing the object to go on a circular pathway, we can now apply these circular quantities and obtain the force using an angular measurement. So we start with Newton's second law, mv squared over r, but we know, okay, wait a minute, linear speed is related to angular speed by the radius. So if we square that, we get v squared equals r squared omega squared. We substitute that in, the radii simplify, and your centripetal force can be written in this format, where instead of a linear velocity and radius, we're now looking at the angular speed and radius, and it's a linear relationship, there's no fractions involved. So your task in this lab is going to be to compare the centripetal force that you measure using this relationship and the hanger force, which is the mass of the hanger times 9.8. The centripetal force apparatus is this big, mean-looking contraption that you can see here. It's a large, heavy base. This base has been placed specifically by the teaching assistants and the lab instructor, so please make sure that you don't dislodge or displace it from its current position. It is balanced according to its current position on the table. The object moves very freely, and you want to make sure when it's balanced, it should not move anytime you place it to a new location. It consists of the base, a photo gate, which you will see is just similar to the pulleys. It has gaps that are evenly spaced that PASCO knows how far apart they are. On top of this rotating arm is the rotating platform, at the center of which is a center post. The center post you see has a spring, an orange indicator disc. It has an adjustable indicator bracket. The top support is also adjustable. The string is tied to the indicator disc, which goes through a hole, fed around a pulley, and connects to this centripetal mass itself, suspended by a string aboard this side post assembly. This centripetal mass, has 3 hooks for the various string connections. The mass is about 200 grams, which you will confirm using a scale. You'll attach a pulley, you'll feed one of the hanger masses over top of it, and then begin your analysis from there.
So over the course of the experiment, you'll have to repeatedly adjust a few of the objects here for collecting the data. So the first step is we have to apply a force, and that force will be known since we'll be using masses, so we know the weight that those will apply under Earth's gravity. And we hook that over the centripetal mass here, and you can see the mass is pulled over and the spring here is extended. So now we have the application of a known force, and we know the amount that our spring is stretched here, so we can compare that with our centripetal. We can compare that with the centripetal force after we take the measurement, since we have no way of directly measuring the force in this lab. So first, after we hang the mass, you have to adjust the location of the centripetal mass at the proper radius. So for this run, we're going to be examining, let's say, the centripetal mass hanging from 14 centimeters. So we move the side post here to where the vertical line on the side post is aligned with the measurement we want. And right here where it meets the ruler, 14 centimeters in this case. So now, to know that this is hanging vertically at the 14 centimeter mark, we have to adjust so the string here, from which it's hanging from the top of the side post, is perfectly aligned with the vertical line on the side post. And also another important thing, so when we're finding the position of the centripetal mass with the applied hanging mass, we should make sure the platform is going to be stationary. You should not be spinning it while the hanging mass is attached. So in adjusting the position of the hanging centripetal mass, we have to use the bracket that the spring is attached to. So we adjust the vertical position of this, and you can see that the position of the centripetal mass moves with it. As I push it down, it moves out. As I pull it up, it moves in. And right here, we are at the position where it is hanging vertically. Have your lab partner hold the apparatus as you're making the adjustments, so it'll be steady, like you can see here. After you have the vertical position aligned, we want to be able to measure the amount of stretch in the string. So we will do that by adjusting this indicator bracket here to align with the orange indicator disc. So this is the reference point then for that amount of force required to stretch the string by this much. So now we're ready to collect our data for this run. So we will remove the hanging mass and the pulley from the experiment.
Thank you, Alex. Once you're ready to collect data, Alex is going to begin spinning the apparatus, and then when we are in agreement that it's ready for it to be data being collected, I'll begin recording the data. Alex? Make sure you don't turn it quite so violently. You'll notice that the spring is slowly shortening and the indicator disc is slowly returning to the indicator bracket. And your partner will tell you when to press play.
Start.
I've begun collecting data because the partner has suggested that that's the best time.
Stop.
And I'm stopping. Launch PASCO as we usually do as soon as it comes up. We're going to once again go over to data, go over to hardware setup, over under the tools palette. Turn off the Bluetooth. It's trying to always look for when it doesn't have data right away. And we click on, so do PhotoGate with pulley, and then we just close that. This time we're not really looking for graphs, we're looking for data accumulation, so we're going to go to drag a table onto the workspace. Select measurement to be time. Select the other measurement to be angular speed in this case. What we're looking for is the average speed. In statistics, we don't refer to it as the average, we refer to it as the mean value. So we'll come up to the sigma, click on the down arrow, turn off maximum, minimum, and standard deviation. We just want the mean in this case. You can keep that information if you like, but for simplicity, all we are looking for is the mean angular speed. And then you click on the sigma, and that should show you the mean at the bottom of the data run. And you can shorten it to help make it more focused. Once your partner is giving it a spin, and they will announce to you that it's time to take data, and when they call it, you click record. So you record this angular speed into Excel for your convenience of doing the calculations later, but you also remember that you have these runs. If you need to look at a previous run, you simply click on run number and go to the run of interest that you have. Remember that you're hitting save, go into file and do save as you do your experiment. Yeah. Once you've done that for your 5 runs, and now you're ready for analysis in Excel. Make sure you copy this information down. You don't even need to export. You can just save your capstone so that it's easy access later.
So to collect for the varying force data, it's going to follow the same procedure, but now instead of moving the side post, we are going to be leaving the side post at 1 radius, and we will be adjusting the mass. For the first run, we did 55 grams with a 50 gram mass plus the 5 gram hanger. Yeah. And for this run, we're going to go down and we will do 45 grams. So the reason I'm going to a lower mass here is because if I were to add more mass, I would have to adjust the top of the spring holder here to further than the experimental apparatus allows. So adjusting the 40 grams, you can see the hanger mass is hanging slightly off to the side. So to adjust it, I will lower the spring platform here. So after we adjust the position of the hanging centripetal mass, now we adjust the indicator bracket again a little bit to line up. Now, since we're ready for data collection, we just have to remove our hanging mass and the pulley. Give it a gentle spin. So now for the analysis, we're going to switch over to Excel, and I'll just show some data and analysis I did from a previous experiment in a previous year. So here we have the mass of the hanging centripetal mass. Over here we have the mass that we hang off the side to apply the force. Here we have the radius where we do the run. Here we have the omega that's measured from PASCO, or the angular velocity. Here's the calculated centripetal force that we use, or that we find from the mass of the centripetal mass, the radius, and the angular velocity. And then here is the weight force from the hanging mass that we find from multiplying that mass by the acceleration due to gravity, or 9.8 meters per second squared. And then we compare the two over here with the percent. So for the comparison in this lab, when you're comparing the force from the hanging mass with the force from the centripetal force, you can choose to compare using percent error or using difference. And we'll just leave that up to you in this lab, but we would like you to justify as to which one you choose. So after taking a few runs, after taking 5 runs or so, and finding whatever percentage you use for comparing, we want you to find the average and see if that average is under 5% to say if this is a significant result, and we can say the two forces are equal.
So that's today's lab activity. I'd like to thank Alex for joining us, helping us out, and talking a little bit about going through the process. As you can see, he's not going to disappear like my wife did last time. So we'll see you in the lab. Thanks. Okay. Well, that sums up today's lab activity. Hopefully, I always say hopefully. So that's today's lab activity. I hope this. I keep doing that. Stop it. This is not a promotion. Bing, and what do you think? That's good? Okay, so for today's pre-lab, you're going to test. You're going to